Morning, everybody. So today we're going to get started in Chapter 9, and we're going to start talking about proton NMR spectroscopy. And if you like dealing with puzzles, you'll love this. Okay? This is all about working with puzzles. And proton NMR spectroscopy is, without a doubt, if you were to ask a group of chemists, this would be the number one technique that they would say that they need to have access to over all others in terms of being able to determine a structure. Up to this point, when we've been talking about reactions and starting with a starting material, reacting it with a reagent, getting a product, doing functional group transformations, how could you have gone into the lab and determined that that reaction actually happened? What techniques have you learned so far in the lab? You could use some type of chromatography. What are the limitations of chromatography? It takes forever. Doesn't really take forever. You're just impatient. Okay. It does take some time, but what else? So if you do a TLC, what do you get? What information do you get? Jack comes in, he's got a reaction, he runs the TLC of the product. What does he get? He gets a dot. And then what do you do with that dot? You do some measurements and you get what value? You get an RF value, right? Does that really tell you anything about that structure? It tells you a little bit. It might tell you whether or not the product is more polar or less polar depending on the RF, right? If the spot doesn't move as far as the starting material, for example, right? So let's say we're doing a reaction and the product moves less than the starting material does. What does that tell us? Less polar? It's more polar, right? So that tells us that we started off with something that's less polar and we created something that's more polar. It gives us some idea, right? But there are a lot of functional groups that are more polar than other functional groups, right? So we get limited information. And when you all were doing TLC and chromatography in lab, right, you all had standards, right, that you used to compare, right? So when you did the tablets or whatever you all were doing, you had standards that you ran and you knew what things were and you could determine based on standards and RF. But you got to have standards. Well, that's great if you got standards. What other techniques have you learned? So there's TLC, you all also learned about GC, right? What else have you learned in terms of being able to help identify structure? IR, right? But what does IR really tell us? Functional groups, right? It really tells us about a functional group. But, you know, the other day when we were doing that demonstration, that oxymercuration, demercuration, there were two possible alcohols I could have gotten. I could have gotten the Markovnikov alcohol. I could have drawn a mechanism that shows that, and that's what I told you you all got, and you're trusting me, right? But I could have just as easily drawn on paper how you got the anti-Markovnikov alcohol, right? The water could have attacked the least substituted carbon, and you could have ended up with that particular alcohol. Would IR have told us anything about that? Not a thing, right? Because both of them are alcohols, and we would have seen a nice, sharp, parabolic-looking peak around 3,300 for both of them, and we wouldn't have been able to determine much about that. Proton NMR spectroscopy allows us to determine structure without the need of having standards. It's complementary to IR. It allows us to determine where the functional groups actually are located, whether it's on a number 2 carbon or a number 1 carbon or a number 16 carbon, whatever. We can determine a lot of information from proton NMR spectroscopy. Proton NMR spectroscopy is, now it's a fairly old technique. But it's extremely powerful. We will only scratch the surface of proton NMR spectroscopy. We will not get into the deep weeds of this technique. There are entire sequences of courses at the graduate level that you can take to learn more and more about NMR spectroscopy and determine structural elucidation. Okay? Now, you all are familiar with NMR whether you know it or not. Everybody in here probably has either had or knows somebody who's had an MRI. You go to the doctor, They put you in this round circle thing. They move you in there, and you hear this clunk, 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 right? They are doing an NMR experiment on you. Okay? Proton NMR is hydrogen, right? That's what a proton really is, H1 NMR. What is most of our body? Water. And what is the biggest component of water? Hydrogen, right? And it turns out that they can use the signals from NMR to determine an image, okay? So, for example, this is what an MRI system kind of looks like. And you're the test subject. You're being put in there. You're the unknown, right? And they can get these nice little images. What's kind of nice about MRI is it's non-invasive, right? They're not actually sticking probes into you, right? We're using radio frequencies to determine an image. This was such an important development that it actually got several people a Nobel Prize in 2003 for physiology and medicine. It's a very important technique. But chemists have been using NMR, which is really nothing more than MRI for molecules, for a long time now. Okay? The bad thing is that we don't get nice little pretty pictures like this. We get data that we actually have to interpret. Okay? You don't just stick a molecule into the NMR and out comes a pretty picture showing you everything. You have to interpret the information that you get. Okay? And that information looks like this. That looks very different from that, doesn't it? That you kind of know that you've got some kind of spinal cord, right? And you can visualize some things, blah, 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 herniated discs. Can't really figure that out here, right? What do you see when you look at this spectrum? You see numbers? What numbers do you see? You see 20 and 60? Okay, what other numbers do we see? We see something called chemical shift, right? This is in ppms. Anybody know what ppm stands for? Parts per million. That's exactly right. Okay? You all will think of it, and I always refer to it as delta. Okay? ppm, delta, it's the same thing. What else can you tell me about it? Just by looking at it. Okay, can we see carbon in a proton NMR? We can't. We see hydrogens, right? I see this peak that has this 60, and I see this peak that has this 20. I also see this peak at 0. This peak at 0 is actually called a standard. It's TMS, tetramethylsilane. It defines 0 for us. We add it to the solution to define 0, okay? It is added to the sample, so we ignore this peak at 0. Okay? We have to add it so that we know where 0 is. But it looks like there's two signals, right? I see two peaks, one here and one here. One of them corresponds to this methyl group. The other one corresponds to these 3 methyl groups. Okay? And so what we have here is methyl tert-butyl ether, MTBE. It's a gasoline additive. We've talked about that before when we looked at making some ethers, right? But this is the spectrum that I would look at to know that I've made that molecule. When I look at this spectrum, I can see MTBE in my mind. You will get to where you can put these things together quite easily. Okay? Can anybody guess as to why this methyl group is further down than these methyl groups? There's only a third, that's true, but that accounts for the integration difference, the 20 and the 60. This is called an integral. How many of you have had calculus? What's an integral? Area under a curve. That's exactly right. The simple definition, right? It's the area under the curve. And the powerful thing about integrals, so I took all this calculus when I was in college too, and I learned that all an integral really is taking a curve, cutting it out off from a piece of paper, and putting it on a scale and weighing it. So you learn all this fancy stuff, and all you have to do is be able to cut it out and weigh it, right? And that's what the machine's doing. So this is like 20 and 60. Think of them as different weights. It's different areas under the curve, right? Because there's 3 times as many methyl groups here as there is here. You can see the 1-to-3 ratio. Okay? So it tells us a lot of information. But this is further downfield because this methyl group is actually, the carbon is attached to oxygen, and oxygen's electronegative, so it pulls the signal further downfield, as we call it, okay? So the closer you are to 10, right, this is closer to 10 than this, the further downfield you are. The closer to 0 you are, the further upfield. So I would say that this signal is upfield of this one, or this signal is downfield of that one. Okay, so we have upfield and downfield that you'll hear me talking about an awful lot. Okay? This is another simple organic molecule. This is, how would we name that organic molecule? Pardon? Bromoethane is perfectly acceptable. What would be another name? Ethyl bromide. We could use either one of those nomenclatures. What's different about this spectrum than the previous spectrum? It does have a halogen, that's true. That's the molecule, but not the spectrum. Pardon? The peaks aren't as clean. What do you mean by that? What about these?
They're just really straight up.
They're straight up. We call these singlets. It's just a single line. But that's not the case here, is it? So these pink ones look like what when we blow it up? We've got 3 peaks. And the blue? We've got 4 peaks. Right? Although we've only got the CH3 group and the CH2 group, but now all of a sudden we're seeing this, what we call splitting, this fine splitting. Okay? And there's a lot of rich information there. We have 2 signals just like we did in the previous one, but now we have other information. Can anybody guess as to why this is what we would call a quartet and this is a triplet? Can anybody guess for me?
The number of peaks.
What do you mean by the number of peaks?
There's 3 of them.
Well, there are, but why are they that way? Huh? So this one you think is 3 because of 3 hydrogens? Then why would this one be 4 if there's only 2 hydrogens? Bromide accounts for the fact that this is further downfield. That's true. Very good. This splitting arises because of the neighboring protons, and we'll learn more about that in a moment. Not only does it tell me the signals that I have, but it also tells me how many hydrogens are near those signals. So this is a triplet. These 3 hydrogens are this triplet because there are 2 neighbors. These 2 hydrogens are a quartet because they have 3 neighbors. You should see that there's a mathematical relationship. The number of peaks that you have is the number of neighbors that you have plus 1. And it's because of statistics. We'll talk a little bit about that later. But by looking at this, I know that there are 2 signals, and I know if I looked at the integration, I would see a 3-to-2 ratio, but I can also tell you how it's connected because of the way that these things are split. Okay? Now, proton has what charge associated with it? It is a positively charged particle, right? Now, you all learned in physics, probably in high school even, that if I take something that is charged and I move it, what do I generate? I generate a magnetic field, an electromagnet. That's exactly right. So if I take a wire, I wrap it around a nail, I hook it to a battery, I've got electrons flowing through that, and I generate a magnetic field. Well, it turns out that protons don't just sit in the nucleus. They're there and they have a spin associated with them, like the Earth. They don't sit still, they spin. So they are charged and they are moving. So the protons that make up the water in your body, right, are actually little magnets. They're very weak magnets, but they are magnets nonetheless. They have magnetic properties, okay? And so just like the Earth rotates, so does a proton. We generate a magnetic field. This is exactly why the Earth has a magnetic field, by the way, because the core rotates. Molten iron rotates, and you generate a magnetic field. And you get these magnetic field lines. Okay? So we're going to talk a lot about magnetism when we talk about NMR. Okay? And we actually deal with some pretty big magnets. And I'll show you one on Monday. So here we have a proton that's spinning, and this little line that you see going up through the axis is called the magnetic moment. Okay? Think back to physics a little bit. Okay? So that's the direction of magnetism, if you will. Okay? Now, if I take this spinning proton and I just place it out here in the room where there's not a strong magnetic field, the magnetic field in this room is weak and it's from the Earth, right? It would turn out that these magnetic moments would be random. You would have things that would lie to the east, the west, north, south, and it would just be a random hodgepodge of orientations. However, if I created a strong magnetic field and I placed my protons in it, I create a situation where the states of these protons are said to be quantized. What do you know about quantum theory? It's either one or the other, right? You can't have in between. And so when I place these little tiny magnets into a strong magnetic field, and this strong magnetic field is just represented as B0. Physicists like to use B0 for some reason for magnetic field, so we just go with it. Okay? There's only two possible orientations. It can either align with the magnetic field, or it can oppose it. It can't be sideways to it or kind of cockeyed to it. It's either up or down. And you'll hear me talking about spin up and spin down. Okay? And so that is oriented. If you count the spin ups and spin downs, what can you tell me? Are they equal? They are not equal. Okay? But are they vastly different? They are not vastly different, but they are not equal. There is one way that you can align that is less energetic than the other. Okay? And we can use this difference to get NMR spectra. Okay? So for example, the lower energy is when the spins are aligned. So this is the direction of the magnetic field. Notice the spin aligns with it. That's lower in energy. Opposing the magnetic field is higher in energy. Okay? It's either here or here. Can't be anywhere in between. And this is an energy difference. Okay? Now the spin quantum numbers that they use for this are either plus 1/2 or minus 1/2 for a proton. And you'll learn a lot more about that if you go to graduate school. Okay? If you're in polymer science, you're going to use NMR a lot. Okay? And you will learn more about it than we could possibly have time to talk about here. Okay? And so we can measure this energy difference. And that energy difference gives rise to the NMR spectra that we're going to be looking at. But it's a quantum thing. It's either plus 1/2 or minus 1/2. Nothing in between. Okay? So we have energy here and we have B0 on the x-axis. What do you think happens to that energy difference as we increase the strength of the magnetic field? Does the energy gap increase or decrease? It increases. That's exactly right. And so for many, many years in the NMR field, there was kind of a magnet race to see which manufacturer could build the largest magnets to do this kind of stuff with. Okay? I've actually worked with magnets that you have to climb up like 2 or 3 flights of stairs to get to the top of. They were that big to work with this. Today they've been able to miniaturize a lot of this, and we have a fairly strong magnet over here in our NMR facility that I'll show you on Monday. Okay? But as we increase B0, that energy gap increases. Is it easier to measure a small energy difference or a large energy difference? A large energy difference. The larger the energy difference I have, the more information I can get about my molecule. Okay? And so people were racing for many, many years to try to build big, big magnets. And in fact, in Florida, I think it's at Florida State, there is the National High Magnetic Field Laboratory, which is a huge building filled with big magnets. You can't go in there if you've got a pacemaker. It's big, big facility. And people go there all the time to use some of the world's largest magnets to do these types of experiments. Okay? Okay, so you can see that as we go up in stronger magnetic field strength, this energy gap gets bigger. This is the equation that if you were in a physics class, I would hold you responsible for. But this is an organic chemistry class. I don't like a whole lot of numbers and math, right? But what I want you to know is that the change in energy is proportional to B0. That's all you need to know for this class, okay? You don't need to know about the gyromagnetic ratio or Planck's constant, all that kind of stuff. You just need to know that the energy gap is proportional to B0, okay? And so we always try to have bigger magnets to do this type of work with. This is kind of what an NMR spectrometer looks like. It is the most unimpressive piece of equipment you will ever work with in terms of how it looks, because it doesn't make any noise hardly. It just sits there. You got a computer and a console and a tin can that kind of looks like R2-D2. All right? It just sits there. Inside is a superconducting magnet, which is kind of cool, literally, because it is immersed in liquid helium. So this is nothing more than actually a big thermos bottle with a magnet inside it. That magnet is sitting in liquid helium. Can anybody tell me anything about liquid helium? It's the coldest substance that we can actually really work with, right? At least in large quantities. It's near absolute zero, right? Why do we need such cold things? What do y'all know about superconducting materials? Huh? They can get hot, and when they get hot, what happens? They quit being conducting, right? And so you have to keep these things extremely cold. Liquid helium is really, really expensive. And so you have this thing immersed in liquid helium, and to preserve your liquid helium, because liquid helium is so cold, we actually have another jacket inside here that's filled with liquid nitrogen, which acts as a buffer between the outside air. So we have the liquid nitrogen boiling off quite a bit, and we have to fill it with liquid nitrogen every week, but we only have to fill the liquid helium maybe once every 4 to 6 months, okay? And it costs several $1,000s a year for us just in liquid helium to keep one magnet active, okay? We have 2 magnets in this department. I think polymer science has 4 magnets. So my guess is it probably costs us somewhere around $50,000 to $60,000 a year to maintain these in terms of liquid helium and cryogens and having people to do that kind of work. But it's a pretty boring little looking instrument. Even an IR is a little more interactive than this, okay? Basically what you do is you just put your sample in up here. It goes down into the magnetic field, and it gets spun, and you'll hear the air pressure come on, and that's about it. And then you sit at this computer and you do the experiment. And it's all automated. So you go click, 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 go, and it does the experiment for you, and in like 5 minutes or less, you have your NMR spectrum, okay? So basically, it turns out that that energy gap that we're looking at is in the radio frequency range. So we place our sample in the tank here, in the NMR spectrometer. We now have an energy gap, and what we do is we hit that sample with radio frequency, and we measure the energy that it takes to go from the lowest energy state to the highest energy state. So if I put energy in, I should be able to populate that higher energy state, right? And then when I populate that higher energy state, I watch it come back down. And what we have is called a free induction decay, or a FID. And you'll hear people in NMR talking about the FID file. And it looks like this. It actually looks like a squiggly line, okay? That does not look anything like an NMR spectrum, does it? But then they do a little math trick on it. For those of you who've had higher level math and have done Fourier transform, it takes the FID and it converts it into your actual NMR spectrometer by Fourier transform, okay? I don't care if you know how to do a Fourier transform. I don't care if you look at a FID and understand what it really means at this point. You'll learn more of that later. I just want you to understand how the technique is working right now, okay? It's all physics. This was a physics experiment back in the day. And the physicists got bored with it, and the chemists figured out it was more useful than the physicists thought, and we stole it from them, okay? And we use this technique all the time. It's really a chemistry technique these days, not so much a physics technique. A couple things that you need to know here on the chart. Protons that are in different environments will absorb at slightly different frequencies, or ppm, okay? So we can distinguish them by NMR, right? Just like in both of those examples we saw two signals. I could distinguish those signals from one another. The frequency at which a particular proton absorbs is determined by its electronic environment. Is that proton on a carbon that's attached to an electronegative atom or not? That determines where that chemical shift is. Is that proton on a carbon atom that's in resonance with something else? That determines where its chemical shift is. Modern NMR spectrometers use a constant magnetic field. We use superconducting magnets, which have a very constant magnetic field. And then we blast them with a range of frequencies, radio frequencies, to achieve the resonance of all the protons. And it's important to know that NMR can only be done on certain elements. Not every element is NMR active. Only elements that have odd mass numbers, like proton. Proton has a mass number of 1, right? Or odd atomic numbers give rise to NMR spectra. So for example, proton has an odd magnetic or an odd mass number, carbon-13 has an odd mass number, fluorine-19, phosphorus-31. These are common elements that we can actually do NMR on. And we're not going to talk about fluorine or phosphorus in this class. We're going to talk about proton today. Monday we'll talk about carbon NMR, because most organic molecules are carbon and hydrogen for the most part, right? So that's what we're interested in. But you can also have odd atomic numbers like deuterium, and nitrogen-14 can also give rise to NMR signals. Okay? Why do you suppose carbon-12 does not give an NMR signal? If you looked at, what's the mass number for carbon? 6. Is that even or odd? Even. I appreciate your bravery, though. And carbon-12, the mass number is what? And the atomic number is? And so it's even, right? But carbon-13 has a what? It has an additional neutron, and what about its, what, we're talking about mass number now, right? So it has an odd mass number. It still has an even atomic number, but it has that odd mass number, and so it can give rise to signals. It turns out that if a molecule has an even mass number and an even atomic number, its nucleus does not spin. You can go talk to the physicists and ask them why. I have no clue. And I don't care, right? I just know that they don't spin. And if the charged thing doesn't spin, it doesn't create a magnetic field. And if it doesn't create a magnetic field, I can't detect it by NMR. Okay? So important for you to know that. The first thing that you're going to need to be able to do, and your model kits are going to be helpful here, you're going to have to be able to identify the different types of protons in a molecule and determine the number of signals that you should see for a particular molecule. So the number of NMR signals equals the number of different types of protons in a compound. Okay? Protons in different environments give different signals. Equivalent protons will give the same NMR signal. Okay? If I look at dimethyl ether, these protons are equivalent due to what? What makes those two methyl groups equivalent? Why are they the same? Okay, that's true. But why does this methyl group, or the hydrogens on this methyl group, have to be that one? I'm looking for something really simple. It is symmetric. What kind of symmetry does it have? Mirror symmetry. There is a mirror plane that runs through this oxygen, and that dictates that the hydrogens on the left are equivalent to the hydrogens on the right. And so if I was to go and run dimethyl ether in an NMR experiment, I would see one signal, and only one signal. If I look at chloroethane, I see two signals. There's symmetry that runs through this, but the symmetry doesn't make these hydrogens equivalent to those hydrogens, right? It just doesn't. It's not mirror symmetry in that way. So I'm going to get two different signals. Now notice in this example, I've got two methyl groups. I've got methyl group HA and methyl group C. They're both methyl groups. They're both CH3s, but they are not equivalent. Why? Exactly. This methyl group is bound to an oxygen. This methyl group is bound to another carbon. There's no mirror symmetry there that says that those two methyl groups have to be identical. So we're going to see three different types of signals. We're going to see HAs, HBs, and HCs. Okay? Now, when you're talking about things that have three-dimensional structure, your model kits are going to be your best friend. So, for example, if you were to look at chlorocyclopropane, you need to think of it in three dimensions. Because looking at it in three dimensions, you will come up with a different number of protons that are not equivalent than you will if you just draw it like this. Looking at this structure, how many signals should we see? Is there any symmetry? There is. There's a mirror plane of symmetry that runs through these two carbons and goes through that, right? And so the stuff on the left and the stuff on the right are equivalent. So how many signals should I see? Think harder about it. Is the top and the bottom equivalent? No. So there's a mirror plane of symmetry, but only one. These are equivalent. These are equivalent. And this is not equivalent to anything else. So how many signals is that? It is three. These will give rise to a signal. These will give rise to a signal. And that one will give rise to a signal. Why is the top different than the bottom? Pardon? The chlorine, exactly. These two hydrogens are on the same side as the chlorine. They are syn to the chlorine. What about these? They're on opposite planes, right? And they will give rise to different signals. You will have to find the number of signals on the next exam. I can guarantee you that. You need to practice this. I will give you a problem where you have to determine the number of signals. Okay? And so you need to be careful how you draw it out. If we think about vinyl chloride, you want to draw it like this so that you can see how things are in three dimensions. Not like this because you can't really tell. But if I look at it like this, how many signals would I expect to get? Pardon? 3. I will see 3. This hydrogen is on the same carbon as the chlorine, whereas these two hydrogens are on a different carbon. Right? So this hydrogen is clearly going to be different than these two. This one is on the same side as the chlorine. This one is trans to it. It's different. So I will see 1, 2, 3 different signals for that particular molecule. Okay? If you were to draw it out like this, I think you would probably argue 2, because you're not seeing it all in 3 dimensions. Okay? So very, very important that you build your models, that you look at things in 3 dimensions, draw things 3-dimensionally. Okay? Because you're going to have to be able to do that. Here we have some other examples. So here we have 1,2-dichloroethane. We're only going to get one NMR signal. What symmetry element dictates that? Mirror plane. I've got mirror symmetry right through these two carbons. Here I have chlorobromopropane. So 1-bromo-3-chloropropane. I'm going to see 3 different signals. Right? Yeah, yes, chlorine and bromine are both electronegative halogens, but they are not identical. So there is not a mirror plane that runs through this. Each one of these CH2 groups is unique. Here we have methyl acetate, okay, or the methyl ester of acetic acid. I've got 2 CH3 groups, 2 methyl groups. but they are clearly different. Why are they clearly different? One's attached to an oxygen, the other one attached to a carbon. They are different. We're going to see two NMR signals. And then our good friend ethanol. We're going to see three NMR signals for ethanol. We're going to see CH3, we're going to see CH2, and we're going to see the hydrogen on the oxygen atom. We will see all three of them. Okay? You can actually use NMR to determine the quality of vodka. That's how they actually do it. They use NMR to determine the quality of vodka. Okay? It's a nice technique to do this with. All right. You're going to feel overwhelmed at the end of the day, and that's okay. There's a lot of information coming your way. You're going to be practicing this when you get into lab. There's an NMR dry lab for you all later in the semester. Okay? But we just got to get through this information. The first thing you're going to do when you look at an NMR spectrum is you're going to count the number of signals to determine how many unique environments there are in a molecule. The very first thing you do is you count the signals. Okay? So if I was to look at this example, we don't count TMS because that's the standard, so we just cross out the thing at 0. How many signals do we see? We see 3 signals. On my exams or on the ACS standardized final that you take next semester, you've just determined that there are 3 signals. Anything that I give you as a choice that should give rise to more or less, those number of signals, can't be the correct answer, right? You've got 3 signals, so if I give you a molecule and you go, well, that should have 5 signals, it can't be the answer, right? So that's the first thing that we do. That's real easy. The second thing that we need to do is use chemical shift tables to determine what type of environments the hydrogens are in. Now, you all can memorize this table. You all can memorize what's in the book, and you will waste all your time for the purposes of my exam. You really only need to know a couple of things. You need to know that a proton NMR goes somewhere between 0 and 10 to 12-ish. Can actually go out further, but this is for most organic molecules. Okay? So you need to know the scale, and you need to know where to draw a line. Just like in IR we drew lines that separated things, here you need to know where to draw lines. The cool thing about NMR is you only have to draw one line. Can anybody tell me where that line needs to be drawn? Nope. Where would you draw a line? Where do things look like they change drastically? Nope, not that gap. 4.5's getting really close. I tell everybody to draw a line at 5. So you draw a line somewhere around 5. And what do you recognize? To the right of that, all of the hydrogens are on sp3 hybridized carbons for the most part, with the exception of sp. So everything from 5 to the right is either going to be hydrogens attached to sp3 hybridized carbons or sp hybridized carbons. Everything to the left of 5 is on what kind of carbon? sp2, or they're acids. So the first thing that I do when I look at an NMR spectrum after I've counted the signals, I actually do this. When we have something that I don't know what the structure is, I draw a line at 5. So if you don't see anything past 5, anything that I give you that has an sp2 hybridized carbon in it with a hydrogen on it, you know it can't be right. Just by simple inspection. What else can you tell me? What you should be able to tell me is that things are pulled further downfield with the more electronegative atoms that are attached that are close to it, right? So if I have an oxygen attached to the carbon that the hydrogen is on, that's going to be somewhere between 2.5 and 4.5. If I have a hydrogen that is alpha to, say, a carbonyl or an alkene, it's going to be somewhere between 1.5 and 2.5. And if it's just on a regular old sp3 hybridized carbon atom with no electronegative atoms, it's going to be somewhere between 1 and 1.5. I have these committed to memory. Of course, I've had 20-some years of working with this. right? But you will too. You'll be able to commit this. But the thing that you have to know is that you just draw a line at 5. Like I told you, NMR goes from about 0 to 10. I know it shows 12. It can go a little further. That's easy to remember. What's half of 10? 5. Draw a line. Okay? And so, again, we've got upfield and we've got downfield. On my exam, you will not need to know chemical shifts to any higher level of precision than this. If I was to give you a real problem, a real unknown problem, yes, you might need to be looking at chemical shifts and know things within 1/10 of a ppm. But for the purposes of my exam, if you can have these rough areas figured out, you're in good shape. You will have a note card on the next exam. What might be a good thing to put on your note card? That right there, right? I am more interested in you being able to solve a problem with that information than you memorizing this information, okay? The third thing you're going to do is you're going to determine the integration of the signals to get an indication of the relative number of protons produced by each signal. That's what integration tells me. What's important there? What word in that statement is important? What's the most important word in that sentence? Relative. Very good. Relative. What does that mean? So if you get an integration of 1 to 3, what does that mean? 3 times. But does that mean it's really 1 and 3? 2 and 6 could be the same, right? It just means it's a 1 to 3 ratio. It does not tell you the absolute number of protons in and of itself. It tells you the relative number of protons. Okay? And that's clear here. If we look back at our example that we've been working on, we know we've got 3 signals. We draw a line at 5. So what can we say about this particular molecule? We don't know what it is yet, other than the molecular formula, right? But we don't know exactly what the structure is. What can we determine? We've got 3 environments. What's the hybridization of all these carbons? sp3. There's nothing sp2 because there's nothing past 5, right? We know that we've got things that are further upfield and further downfield. So there's, when we know that there's the electronegative atom, so that makes some sense, right? But now we also know the relative number of protons, 1 to 1 to 1.5. What's weird about that number? You can't have half a proton. So what do I need to do with this information? Multiply everything by 2. So it's really 2 to 2 to 3. And if I add that up, what number do I get? 2, 2, and 3 is 6. It's early in the morning for math, isn't it? 7, right? And how many protons do I have in the molecule? 7. So I just converted this into the actual number of protons. This signal, it represents 2 protons, probably really close to the bromine, right? This signal represents 2 protons, a little further away from the bromine. This signal represents 3 protons, the furthest away from the bromine, right? The last thing you're going to do is you're going to interpret that splitting pattern. This is going to be the most challenging part for most of you. If I have 2 protons, A and B, that are adjacent to one another that are not equivalent, okay? These are non-equivalent because they've labeled them A and B. Yes, I know there's a mirror plane through there, but these don't mean anything, okay? You will see a pair of doublets. HB will be a doublet because it has 1 neighbor. HA will be a doublet because it has 1 neighbor. Okay? Neighbors are adjacent protons that are vicinal to one another, meaning on adjacent carbons. Okay? Here, we will have a triplet and a doublet. This CH2 will be a doublet because these 2 protons are equivalent, and they have one neighbor. So they are a doublet. This proton is different than these protons, so it gives a different signal, but it has the two neighbors, so it will appear as a triplet. This is called the n+1 rule in splitting. N is the number of neighbors plus 1. HA has how many neighbors? It has 2. 2 plus 1 is? That's why it appears as a triplet. Okay? It acts, for those of you who like math, it actually follows Pascal's triangle. So think about that. That'll hurt your head. Here we have a triplet of triplets. Here we have a quartet and a triplet. And here we have a quartet and a doublet. I'll let you go through those, but they all follow the n+1 rule. They tell us how many neighbors they have. I have a signal that's a quartet. I know that that signal has so many protons because of the integration, but the splitting tells me how many neighbors are close to it, right? So I can get a lot of information from this. So now when we look at our example, we know that we've got 2 to 2 to 3. How can I put 3 carbons, 7 hydrogens, and a bromine together to get a spectrum that looks like that?
So I have a question. How do you determine the integral? Do you just kind of eyeball it?
You do not eyeball it. The computer actually spits it out, the number.
It would be given to us?
It would be given to you. But the integration is the height distance from here to here. Okay? And so when I was an undergraduate, we still had an old NMR that didn't have a fancy integration system. It just drew these lines, and you actually took a ruler out and you measured it in millimeters, and that's how you determine the integration. But today, you get these lines, but the computer actually spits out the integration for you. So how can I put 3 carbons, 7 hydrogens, and a bromine together to give that spectrum? See if you're right. Whoop. Yeah, you're very much so right. Right? So, these 3 are this. How many neighbors do they have? How many neighbors do these 3 have? 2, so it's a triplet. And it's going to be the furthest upfield because it's furthest from the bromine. How many neighbors does this CH2 have? It's got 5 total, so how many peaks should it be? 6. So I'm just going to put a 6 up there. And it's going to be a little further downfield, right? And if you look at this one, 1, 2, 3, 4, 5, 6 peaks. And then this one will be a triplet because it's got 2 neighbors, and it's going to be the furthest downfield because it's actually attached to the carbon containing the bromine. Okay? So, we will finish up with this on Monday and get started on the other stuff. Have a great weekend.